Albert Einstein or Isaac Newton. These two are the most popular scientists in the world. Who was the bigger genius?
Einstein was a lot smarter than Newton.
No, actually, if you want to put them head to head, I think I'd put Newton ahead.
Einstein comes next after Newton.
My favorite physicist is Isaac Newton.
If Newton were around in Einstein's time, Newton would have done it all. If Einstein were around in Newton's time, not so much.
These are some of the most popular scientific minds of today's generation, and all of them have declared Isaac Newton an unrivaled genius, meaning a genius like him has never been born till now. In fact, Einstein himself wrote in his autobiographical notes that Newton was a creative genius of the highest order. But such a brilliant scientist, whose theories were considered unbreakable for 200 years, and even today, we are taught Newton's laws of motion in schools and colleges. Einstein only gets mentioned much later in degree colleges. But ironically, the first person to challenge Newton was none other than his deepest admirer, Albert Einstein. Well, let's do a small experiment. If I drop this ball from my hand, what will happen? Well, according to Newton, the ball will fall down and hit the ground. Because of gravity, which is a force that attracts two objects to each other, like the ball and the Earth in this case. But according to Einstein, this is wrong. Gravity isn't even a force. In fact, gravity is just an illusion, a deception, and the ball isn't even falling down. Instead, the ball is actually standing still in its place. So then, is the ground moving up? And let's talk about one more thing. Let me ask you this. If I place a ball on a table, tell me, is this ball in inertia, or is there some force acting on it? In physics, inertia means an object's tendency to retain its current state. If it's in motion, it stays in motion. If it's at rest, it stays at rest. Until and unless some external force acts on it. So, in the example of the ball placed on the table, well, Newton would say it's in inertia because it's at rest, but Einstein would say there's a force acting on it, acceleration. In fact, when you let go of the ball with your hand, that's when the ball actually comes into inertia. Well, you'll find plenty of such contradictions if you compare Newton's and Einstein's theories side by side. But in the end, through his special and general theory of relativity, Einstein proved Newton's theories to be incomplete, and today, that's what the world accepts. So, if Einstein actually proved wrong the very thing that Newton is most famous for, gravity itself, then why did Einstein still consider Newton to be, without a doubt, the greatest genius in all of history? Was he just trying to be humble in his autobiography, like when Magnus Carlsen, the highest-rated chess player in history, was asked who the best is, and he skipped his own name and instead mentioned his inspiration, Garry Kasparov? I think Garry is great for all times. And was everything we were taught about gravity as kids actually wrong? Well, friends, today in this video, we'll find out exactly why we're still being taught Newton's theories, even though the world knows they're incomplete. What exactly were the flaws in Newton's laws of motion, his mathematics, and his explanations that Einstein noticed and fixed? We'll even find out how the experiment often shown to visualize Einstein's gravity can actually be misleading, which might be the reason you're not able to fully grasp gravity. And finally, what did Einstein see in Newton that made him call Newton an even greater genius than himself? By considering all of this rationally, we'll be able to better judge who was the greater genius between the two. So get ready, because this video is going to challenge your understanding of reality in a big way. So let's get started, shall we? About 400 years ago, in 1633, the Roman Church threatened Galileo Galilei that if he didn't stop promoting his scientific ideas, he would be sentenced to death. Galileo's discoveries were proving the things written in the Bible and the beliefs of that time to be wrong. Back then, people believed that our Earth was the center of the solar system and that the sun and all the other planets revolved around it. This model is called geocentrism. But Galileo himself saw 4 moons of Jupiter through his telescope, which were orbiting Jupiter. This meant that not everything was revolving around the Earth. He also observed the different phases of Venus, which meant that it too was orbiting the sun. This was direct proof that Copernicus's heliocentric model could be correct and the Church was wrong. But the Church was not willing to accept this truth. And that's why, in 1633, Galileo was sentenced to life imprisonment for spreading false knowledge and going against religion. We declare that you, Galileo Galilei, we condemn to formal imprisonment in this holy office at a later date. He was banned from publishing research, writing books, and teaching science, and in 1642, after suffering the consequences of speaking the truth, he died. But as they say, the truth can never be suppressed. It can never be hidden. Call it a coincidence or something else. In that very same year, 1642, on exactly Christmas Day, a person was born who would one day bring this suppressed truth to light for everyone. It was as if Galileo had been born again, but in a different body, because this person was none other than Isaac Newton, born in Lincolnshire County, England. Sir Isaac Newton was born at a point in history when the subject of science had just begun, when only its ABCs were being learned. Newton came from a troubled family. 3 months before he was born, his illiterate farmer father had died. When he was 3 years old, his mother married a wealthy man who didn't even want to accept Newton as his own. Because of this, Newton spent his entire childhood with his grandparents in the absence of his mother, and this feeling of abandonment may have been the trauma that made his personality so unique. Being completely aloof, not trusting anyone, holding on to things, being extremely obsessive, seeking revenge. These are some of Newton's dark personality traits that you'll find mentioned throughout his biographies. For example, later on he made a list of his sins, in which he expressed his teenage thoughts. In that list, he wrote that at one point he was so frustrated that he even had thoughts of burning his mother and stepfather. But anyway, within a few years his mother got divorced and she came back to live with Newton again. When he was 15, she wanted Newton to quit his studies and work on the family land as a farmer. But Newton was made of something entirely different. In fact, even while working on the farm, he would often sit under a tree and solve math problems. Seeing Newton's talent, his school headmaster convinced his mother to let him go to Cambridge for his studies. And that's where Newton's journey to greatness began. I mean, Newton's headmaster played such a huge role in his success. In recognizing their capabilities and giving them the right direction. We were discussing what happened at Cambridge that marked the beginning of Newton's journey to greatness. As soon as he entered college, he realized within a few days that they were teaching outdated concepts here, like physics from Aristotle's time. According to Aristotelian physics, there's no such thing as gravity. Every object just has a natural tendency to move from a non-rested state to a state of rest. For example, when you drop a ball, it falls to the ground and comes to a state of rest. The bigger the object, the stronger its tendency to come to a state of rest. Now let me ask you a common sense question. Give me the answer to this. I take 2 balls, one with a lot of mass and the other with less mass. If I drop them both from above at the same time, which ball will hit the ground first? What does your common sense tell you? Well, according to Aristotle, the ball with more mass will have a greater tendency to come to a state of rest, and that's why the heavier ball will fall to the ground first. But Newton couldn't digest this idea. Actually, there was another thing about Aristotelian physics of that era that Newton couldn't accept. The claim was that an object needs a constant force to keep moving forward. If you stop applying force, the object will also stop moving and come to a state of rest, because remember, every object naturally tends to remain at rest. That means Aristotle didn't even have the concept of inertia. So, no concept of gravity and no concept of inertia. Now, why wasn't Newton satisfied with this? Because one of his inspirations, Galileo, had already demonstrated in 1589 with an experiment from the Leaning Tower of Pisa that when 2 balls are dropped together, they actually fall at the same time regardless of their mass. So whether an object's mass is greater or lesser doesn't really have much to do with which one falls first. And that's why, driven by his passion to seek the truth on his own, Newton began to self-study the books of modern thinkers and scientists like Galileo, Copernicus, Descartes, and Cavalieri. Just imagine, you go to college and within a few days you realize they're teaching outdated concepts, so you start studying on your own instead. Scientists who think like this end up doing something truly extraordinary. He even created a special notebook called Questionum Quodlibet Philosophiae, which means certain philosophical questions, where he wrote something truly beautiful. Aristotle is my friend, Plato is my friend, but my best friend is the truth. After 4 years of self-study during his university days, Newton began to gain clarity about the concepts of motion and gravity. When Newton saw things falling down, two powerful thoughts came to his mind, and both of these thoughts later led to two major inventions. The first thought was, hey, the way things fall downward, could this tendency be because of some force? And could it be that this same force is what keeps our moon in Earth's orbit? By that time, Kepler's laws of planetary motion had already been invented. And that's why Newton knew that the moon revolves around the Earth in an elliptical orbit, but no one knew why. For some reason, it was just assumed that it does. So Newton just had to somehow demonstrate conclusively that the same force that pulls the apple down is also, in other words, what keeps the moon revolving around the Earth. And that's how the concept of gravity was discovered. Now, this idea never occurred to anyone, not the philosophers from Aristotle's time, nor Galileo, nor Copernicus, that a force which attracts two objects to each other could be what makes the moon revolve around the Earth. Why doesn't the moon crash into the Earth? Well, let's understand this with one of Newton's thought experiments, the example of Newton's cannonball. If you shoot a cannonball from the Earth with a low force, the Earth will attract it downward and it will fall to the ground. And if you shoot it with a lot of force, it will cut through Earth's atmosphere and fly off into space, just like rockets do. But if you applied just the right amount of force, so that the Earth can't pull it down to the ground, but it also doesn't have enough forward acceleration to fly straight off into space, then it will just keep falling forever. But it will never actually touch the ground of the Earth. This is what they called an orbit, that the same force that pulls things down is also what keeps the moon revolving around the Earth. Now, they just had to prove this mathematically. So, how do they do that? Just wait and watch. But before that, the second thought that came to them while watching things fall was that as soon as an object falls, we can easily measure its falling speed using the distance upon time formula. But the problem here is that this formula only lets us calculate the average speed of the object as it falls through the air. If, let's say, we want to know the exact speed or velocity of the apple at the precise point exactly 2 seconds after it starts falling, then how can we actually calculate that? Now, to answer this question, he literally invented an entirely new kind of math, which is used in about 80% of physics today. Calculus. Physics is all about change, and calculus describes change. In the universe, the only thing that's constant is change. Calculus is a mathematical tool that predicts how something will evolve by taking those very changes into account. Calculus describes motion, like the equation of a falling object. Calculus describes electricity and magnetism, like Maxwell's equations. Calculus describes general relativity, like Einstein's field equations. Calculus also describes quantum mechanics, like in Schrödinger's equation. Calculus describes thermodynamics too, and so much more. So Newton had basically learned how to mathematically describe the motion happening on Earth. Now, he just had to learn how to mathematically describe the motion of planets in space, so he could prove that gravity works the same way on Earth and throughout the entire universe. It is a universal force. And then, after several years of hard work, he finally developed the universal law of gravity by corroborating the motion of falling objects, the motion of the moon, and Kepler's third law of elliptical orbits. This is the equation, which is also called the inverse square law. Now, one point to note is that even though Newton developed this universal equation, the idea of the inverse square law was actually older. Newton gave credit to Borealdus and Borelli, who had already hypothesized that there is a force from the sun whose impact halves with every square of the distance. But no one was able to connect these ideas and mathematically prove them the way Newton did. Only Newton could do it, because he was a mathematical genius. And from this, we learn one more thing. In my opinion, scientific discoveries are about 60% imagination and ideas, and 40% math, which helps to prove those ideas. Ideas give direction, and math takes you there. And that's why Einstein also said, imagination is more powerful than knowledge. So never let your imagination stop. With these learnings, Newton later published his 3 laws of motion in his book Principia Mathematica, along with the concept of gravity. This book established such a strong framework for modern physics that Newton's book became like the Bible of science. And after completing his work, Newton passed away peacefully on March 31st, 1727. Now, after Newton's passing, in the beginning, scientists were able to use Newton's model quite well to predict the orbits of planets in our solar system. However, cracks in Newton's theory started to appear when a small planet, Mercury, was not obeying Newton's laws as expected. Mercury's orbit, in particular, could not be accurately predicted with the Euclidean model, despite repeated attempts and careful calculations. Every time, the calculations would go off by approximately 43 arcseconds per century. Was there perhaps a hidden planet whose gravity was interfering with Mercury and messing up these calculations? Something similar occurred to Urbain Leverrier in 1846, who proposed a missing planet called Vulcan. But this missing planet Vulcan was never seen by anyone. And because of this significant calculation error, questions and doubts soon started being raised and discussed about Newton's well-established theory. You won't be able to achieve anything in life. I understood. Nothing. These were the words of one of Albert Einstein's teachers, who was frustrated with Einstein's stubborn attitude. Today, the whole world considers Albert Einstein a genius. But when he was a child, hardly anyone would have thought that. Well, Einstein's childhood was quite interesting. He hadn't even learned to speak until he was 4 years old. His parents were worried that he might have a speech defect. Even today, when children take longer to start speaking, it's often said that they have Einstein syndrome. As a child, Einstein was very quiet and lost in his own world, often daydreaming. He was average in his studies, but he really disliked the rote learning system and unnecessary rules at school. He thought of school as a prison, where children are made narrow-minded and their imagination and creativity are suppressed. Because of this attitude, some teachers didn't like him. But while Einstein didn't like memorization, he loved asking curious questions, doing thought experiments, and learning math. And that's why, by the age of 12, he had taught himself advanced math like calculus and even geometry. Between the ages of 12 and 14, he even started conducting real experiments, like calculating the speed of sound by timing echoes, building model flying planes, and making steam engines. During that time, there was one question that really bothered him, a question that would go on to change his entire life. He was absolutely fascinated by the concept of light, and that's why he often wondered if somehow he could turn himself into a beam of light and travel across the entire universe. What would he see from his own point of view? What would the universe look like? Once again, imagination. He also used to think a lot about time. Why is it that time fundamentally only moves forward in one direction? Now, it's very important to understand the circumstances of that time, because only then can we understand where Einstein got the inspiration to become Einstein. So at that time, there were 2 theories of physics that formed the backbone of our understanding of reality. One was Newton's laws of motion, and the other was Maxwell's laws of electromagnetism, which James Clerk Maxwell introduced in the 1860s. These laws reveal that light is nothing but electromagnetic radiation, and they describe the motion and propagation of light. Now, at that time, there was no proof, but Maxwell's equations were indicating that the speed of light should always remain constant for every observer, which is approximately 300,000 kilometers per second. It doesn't matter whether the observer is in motion or stationary. Okay, let's understand this with an example. Let's say you're traveling in a spaceship at a speed of 200,000 kilometers per second, and there's another spaceship standing still in front of you. Now, if you shine a beam of light from your accelerating spaceship at that speed of 200,000 kilometers per second, how fast will the observer in a stationary spaceship measure the speed of light? Well, Newtonian common sense would say that the speed of light, which is 300,000 kilometers per second, plus the velocity of the spaceship, which is 200,000 kilometers per second, equals 500,000 kilometers per second. Isn't that simple? I mean, if you had launched a missile at a speed of 100,000 kilometers per second, then the missile's velocity would be added to the spaceship's velocity, and the net velocity would come out to 300,000 kilometers per second. By the way, I'm intentionally using speed and velocity interchangeably here so that more people can understand, because speed is a more common word. So this is simple Newtonian relative motion, where two speeds should add up. But that's not the case when it comes to light. The observer will always see the speed of light as constant, that is, 300,000 kilometers per second. In fact, the speed of light will always remain absolutely constant for every observer, no matter what. Now, because light is an electromagnetic wave, Maxwell's equations were making another interesting claim, that a beam of light must travel through some sort of invisible medium. For example, just like sound waves travel through the medium of air, through what medium does light travel? Well, at that time, this medium was given the name luminiferous ether, or simply ether. But the problem was that no one had ever seen ether, nor had anyone proven its existence, which was then tried to be proved in 19987 by two American physicists, Albert A. Michelson and Edward W. Morley. And to their surprise, they set out to prove its existence. But what they actually proved in their groundbreaking experiment was that no such medium as ether exists, and yes, they also definitively confirmed Maxwell's claim that the speed of light indeed remains the same for all observers. Now, how exactly this experiment was proven, and the complete, detailed story of all these events, I've already covered in this video, which you can watch if you want a more detailed perspective. For now, we'll just focus on the main points. So now we've finally reached that point in history where a lot of questions started being raised about Newton's theories. If Newton says that all motion is relative, meaning velocities add up like we saw earlier in the spaceship example, then that doesn't fit with Maxwell's claims. How did Michelson and Morley manage to prove that the speed of light is actually constant? Why doesn't it add up like it does for other things? Is light special? And this is precisely when Einstein enters the story, and the special theory of relativity truly begins, where Einstein considered light to be that unique and special element. In the year 1905, Einstein published a groundbreaking scientific paper to clear up this very confusion, and it changed the direction of the entire physics community forever. The paper was called Electrodynamics of Moving Bodies, and in it, he basically rejected the entire concept of the ether. Along with this, he also pointed out some rather glaring faults in Newton's laws. In this paper, basically, Einstein threw out the ether and replaced it with a very new and truly fascinating concept, space-time. So basically, what we see all around us and throughout the universe as space is not just space, but actually space-time, which is made up of 3 dimensions of space and 1 dimension of time. Space and time are fundamentally connected to each other. They are inseparable. There can be no space without time and no time without space, according to Einstein's model. This was a totally groundbreaking idea that went against Newton's theory. In fact, going forward, Einstein would go on to publish one concept, idea, and theory after another that would expose the incompleteness of Newton's theory. So, what exactly were those ideas? So now, let's move away from the story and do a direct one-on-one comparison. Let's look at the world from the perspectives of Newton versus Einstein, because sometimes the views of these two scientists seem completely opposite. In school, we're taught Newton's laws, but then later on, why does Einstein say that Newton was wrong? So, who should we trust after all? And Einstein, challenging Newton's ideas, said that the apple doesn't actually fall down. Instead, it's the ground that's accelerating. So how can the ground accelerate from all sides? Also, very few people know that there are actually 2 types of gravity. One is real and the other is fake. And the gravity that you and I experience is actually fake gravity. All these concepts are truly fascinating. And don't worry, I'll cover all these mind-blowing concepts that shape our reality in detail in the next and final video of this series.